this to Diane. He's probably the only person who'd understand.
Where did I put my mark?
Can't even
Okay.
comprehend what I'm trying to say.
So we finished 2.3 last time, right?
Yeah.
Okay. So sequential compactness 2.4. That's what we're doing today. So first we need to understand the idea of a subsequence. So what is a subsequence? So let's write out some sequence. And we'll have it be 1 over n, right? 1 over 1, 1 over 2, 1 over 3, 1 over 4, etc. There's some sequence. How do you create a subsequence from this? The intuition is pick a term, and then pick a term after it, pick a term after it, pick a term after it. So a subsequence I might make from this thing would be the subsequence 1/2, 1/8, 1/32, 1/194th, and keep on going. Right? That's a subsequence. Everything that's in here is in here. And the terms come in the same order. If 1/8 came after 1/2 in here, then 1/8 came after 1/2 in here. Does that make sense? So that's the idea of a subsequence. Now I'll write out the exact definition of it, and you'll see it's capturing that exact same idea. Just want to get intuition first so you don't get lost in the notation of what we're doing here. So definition. What do we have? Let AN be some sequence comma, and let n sub k be any sequence of increasing natural numbers. So what do we mean by increasing? I mean n sub 1 is less than n sub 2 is less than n sub 3, etc. Right?
What's the definition?
Well, that's not the definition yet. We're setting it up. Then the sequence
A sub n sub k.
B sub k where B sub k is equal to A sub n sub k is a subsequence of A sub n. Kind of a big definition. And that's the general notation that we use. The general notation that we use for a subsequence is this. A sub n sub k. That's the general notation that we use. So let's wrap our heads around this one more time and make sure we're making sense of it. So I start out with some sequence an. Right? Start picking, you can think about these as indices. Start randomly picking indices. Just make sure that as you pick those indices, it gets bigger and bigger.
And they're all natural numbers.
Yeah, so pick 2, then 7, then 31, then 86, doesn't matter, as long as the indices are increasing. So then whatever these indices are, go and pick the terms from this at that index. That's what this is saying.
Oh, that's the new
What's the kth term in B? It's the n sub kth term in A. So let's write out an example of all these things real quick. So an example of a sequence, once again, A sub n, we could make equal to 1 over n, right? So we have 1 over 1, 1 over 2, 1 over 3, 1 over 4.
And then you create a new sequence that is n's randomly bigger than each other. Not necessarily randomly. But
Not necessarily randomly, but just increasing, doesn't matter.
yeah.
Now make a new sequence, n sub k, where you start picking natural numbers that increase. 1, 3, 4, 6, 8. All it matters is they keep increasing. Then b sub k, using our definition, or a sub n sub k, same thing, is equal to, let's see, this is n sub k, so a at 1 was 1 over 1. A at n sub k3 was 1 over 3.
So are you saying
1
n sub
over
k
4, 1 over 6, 1 over 8.
is n sub k your, like,
Here's n sub
term?
k. It's just increasing natural numbers. It's like picking the indices. So here I've got a sub n. I'm like, which indices do I want to create a subsequence from? I'll let you use the first one, the third one, the fourth one, the sixth one, the eighth one, whatever.
So you're just choosing, you're basically choosing the term in a sub n.
Yeah, the one at that index. This is the first index, the second index, the third index, the fourth index.
Okay. Now my other question is, what if it was decreasing? Is there well, I don't know.
This is the definition of what a subsequence is.
Okay. Can
The-
it ever be decreasing?
No, it doesn't make you can't get an infinite sequence that way. Because you're picking indices. The indices need to go up. You need to be going this way. We don't go from the end of the sequence and go this way. Because what's the end of the sequence?
Oh, okay.
So it's harder to think about it.
Maybe nothing.
So you start picking terms that are increasing. So I pick this one. So it's like I'm going through the sequence from left from right, picking terms. And whichever ones I pick, we write its index down here, right?
Okay, and even if they were negative, like, okay, so say
It doesn't
B sub n
matter
was
that these are
negative.
positive or negative. These numbers always have to be positive because they're the index that this is at.
Okay,
Does that make sense?
yeah.
These are indices. Make sure that's clear. You know what I mean by the index? It's the position we're choosing. So I'm coming along here, I'm like, oh, I'll pick this one. That was at index 1. Oh, I'll pick this one. That was at index 3. I'll pick this one. That was at index 4. Pick this one. That's at index 6. Pick this one. And keep going, just picking ones. Right? Forever. The positions that they were at, write them right here. I picked the one at the first position, at the third position, at the fourth position, at the sixth position, at the eighth position, right? So, a sub n sub k is a sub whatever n sub k is. So the first n sub k was 1. What's a sub 1? 1. The next n sub k was 3. What's a sub 3? 1/3. The next n sub k was 4. What's a sub 4? 1/4, etc. So we created a subsequence, a sub n sub k, from a sub n.
Can you just think of it of your n sub k's as x's and your a sub n as y's? Right, because they're coordinates.
They're
coordinate.
not necessarily coordinates. We
Well,
could
yeah.
represent it, right?
Yeah, but they correlate, right? Like that.
Yeah, kind of. It's better to think about in terms of indices, though.
Yeah.
Far better. N here represents the index that gives you a particular a sub n. K here represents a particular index that gives you an n sub k. N sub k here represents a particular index that gives you an a sub n sub k.
Right.
Good?
Yeah, so that's the definition of BK.
So yeah, that's the definition of a subsequence. That's what a subsequence is. And notice, when does the subsequence end?
When you stop picking indices, probably.
This is a sequence.
So
It goes on for, it's infinite, right? A sequence is infinite. It maps every natural number to something. How many natural numbers are there? Infinite. So it maps infinite things to infinite things. So this goes on forever, so this goes on forever. I'm just trying to set intuition for you that if this gets closer and closer to something, does this get closer and closer to something?
Yeah.
Do they get closer and closer to the same thing?
Yeah.
Yeah.
Yeah. That's going to be one of the things that we prove.
Is the subset of
If you have a
Yeah,
convergent
subsequence.
sequence, any subsequence converges to the same thing that that sequence converges to. But we'll get there. And we'll get there right now. So that's the exact proof that we're going to do. We're going to prove that. I don't know why I raised that, just right here. Prove that every subsequence of a convergent sequence converges to the same thing. Let's write that out using different language. That's a grammar proof. Proof. Will you double check I hit record on that? I don't remember doing that.
Yep.
Yes, okay. Okay, if the limit of a sub n is equal to a, then every subsequence of a sub n converges to a. Understand what we're trying to prove? Alright, so let's prove it. 1. Let a sub n sub k be a subsequence of a sub n. So grab any subsequence of a sub n, call it a sub n sub k. Right?
Yeah.
Now we need to prove that this converges to a.
Well, we know that AN converges.
And we know that an converges to a. So we get to use that fact, and we need to prove that this converges. Now I want to prove that this converges. How do we do that?
I got the definition.
The definition, I need to pick any positive number epsilon, show that for that epsilon I can find an index such that from that index onwards this thing is always within epsilon of a.
Yeah.
Okay.
So that's where we're going. So 2, let epsilon,
The second.
let epsilon be any number greater than 0. Good? Now, remember what we know. We know that a sub n converges.
So we can write it
That means that then there exists some big N in the natural numbers such that
A minus
an minus
A
a
is less than epsilon.
is less than epsilon for all n greater than or equal to
Index.
our big N, right? Observe that
Our little n.
n sub k is greater than or equal to the k for all k in n.
Wait, isn't k greater than n of k?
No, here's what I'm saying. So, shouldn't have erased those things. When we were picking our indices before, the smallest number that we could have picked for that spot is the number itself. In other words, so when I'm picking my indices for n sub k, right?
Yeah.
I could pick 1, 2, 4, 7, 8, 9. However I pick them, the smallest thing I could have put here is 1. The smallest thing I could have put here is 2. The smallest thing I could have put here is 3. The smallest thing I could have put here is 4. And so whatever position we're talking about, whatever k position we're talking about, the n sub k there is greater than or equal to k. Does that make sense?
Yeah.
So 7 would be the n sub k, right?
Well, look, this is k sub 1, or n sub 1. This is n sub 2.
Yeah.
This is n sub 3. So this is when k is 1, this is when k is 2, this is when k is 3, this is when k is 4, this is when k is 5, this is when k is 6.
Yeah, I see it.
So n sub k
It's greater than or equal to.
is always greater than or equal to k. The number is always greater than or equal to the index that it's at. Right? I don't know. Can I just, we'll see what you guys say.
Totally makes sense because k is a bigger number than n, and for all n to that point converges, so obviously for all k that converges.
Yeah. So the sequence, so there came an index in this sequence where from that index onwards, this was less than epsilon, right? N sub k is always going to be further in the index than k was. So however far a sub n was, a sub n sub k is further.
Okay.
I should have kept this in right now. Let me rewrite this out one more time. Where a sub n is equal to 1 over 1. How far did I go? 9? Shoot. 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, 1 over 8, 1 over 9, etc. And then our a sub n sub k, in this example, is 1 over 1, 1 over 2, 1 over 4, 1 over 7, 1 over 8, 1 over 9. Okay, so here's what we're saying. So let's pretend epsilon is what for our example here?
4.
Let's say it's 1/4. Okay?
Okay.
So we're saying, look, in this sequence, from the 4th index onwards, this thing is less than 1/4.
Yeah.
Which means for sure that in this sequence, from the 4th index onwards, this thing is less than 1/4. Because the 4th index of this thing is the same as the 7th index of that thing.
Right, makes so sense.
So whatever the 4th index is of this thing, it's always going to be further along or the same far as the 4th index of this thing.
Okay.
Further along or the same far.
Yeah, I can make a subsequence that's the exact same as this. Right? So if I make this the same as this, then its 4th index is the same as this thing's 4th
And
index.
it's equal, yeah.
But if I don't make this the same as this, then its 4th index could be something different than this thing's 4th
But
index.
the distance is.
But it's either going to be, this thing's 4th index is either going to be 1/4 or something past 1/4. I can't have this thing's 4th index be one of these numbers.
Yeah.
Right? That's what we're saying. So whatever is at a n sub k, 1/7, is further in the sequence than whatever was at a sub n, 1/4. You see that? So when we put 4 in for this, for n up here, we get 1/4. When we put 4 in for k up down here, we get 1/7, which is further along. So if the distance from big N onwards in this is less than epsilon, then the distance from big N onwards in this is definitely less than epsilon. Because it could have only gone further in the sequence. Is that clicking? So I think we're good there.
That makes sense. Question though, if
Yeah.
you have a sequence that your sequence ends up being 1, -1, 1, and you take a subsequence of that, how? Oh, it doesn't converge.
Right, every convergent sequence.
I don't like how you said that, and I don't know what I don't like about it.
About which one?
Your last line saying that that's true for all k greater than n.
So here's the crux of it.
N sub k is always greater. Yeah, I get that completely. For all k.
For every natural number you
yeah,
put
yeah,
here,
right.
this is the case. So whatever natural number satisfied this, the same natural
That
number
natural
gets
number.
further on here. I don't know what else to write in there to help it make sense.
Yeah, I don't either. I can't think of a better way than that.
And maybe the author explained it better.
It feels weird. For all k, that natural number is bigger. And this is true for all natural numbers bigger than the n. We're saying n sub k is definitely bigger than n.
Right.
Okay.
So, well, no, I don't want to say that. Yeah, I don't know what to add.
Just feels like there's a disconnect between n and k. I don't know that n sub k is greater than n.
Remember, n is just a natural number.
Right. So n
So
and
now
k
we're
are
like,
the
now we
same
need to use a k here,
to represent natural numbers.
To represent our natural
N
numbers.
before, okay.
right? Here's the index, here's the term. Now we're saying here's the index, here's the term. Now we're saying here's the index, here's the term.
Yeah. I don't see how else to write it.
All right, so now let's do a little proof using this new knowledge. What?
Saying you're gonna have to use monotonically decreasing.
When you say
Uh,
something with
oh my
monotonic,
God,
you're
oh my God.
supposed to say it.
So,
I was trying.
if a sub 1 is equal
You
to
raised your tone on decreasing.
1, and a sub n plus 1 is equal to 1 plus a sub n over 2 plus a sub n, then the limit of a sub n is equal to negative 1 plus the square root of 5 all over 2.
Easy.
Okay, so first off, let's get comfortable with what this sequence is. What's the first term in the sequence?
1.
1. What's the second term in the sequence?
You plug in.
Plug in 1 for a sub n right there.
Yeah. No. A sub 2. Oh, right. Yeah.
A sub 2
Okay, I see.
equals 1
It's
plus
gonna be
a sub
2
1
over
over
3.
2 plus a sub
3.
2
What do you
thirds.
mean a sub 1? Why are you plugging a sub 1 in for a n?
A sub 1 equals 1.
Okay.
Now what's a sub 2?
And
A
plus
sub 2 is equal to 1 plus a sub 1 over 2 plus a sub 1.
Yeah, why are you doing a sub 1?
James, that's
What's a sub
n
1?
plus 1.
Okay.
A sub 2, are you good with the logic here?
No.
Look before the
A
equals.
sub n plus 1. The next term
N
is
plus
equal to 1 plus the previous term over 2 plus the previous
Okay.
term.
There you go.
Now I see.
So we get our first term in the sequence,
Mhm.
and then here's how you get every term after that. That's what was holding up?
Mhm.
Okay, so now you go with 2/3?
Yeah.
Alright, what's the next term after that?
3/4.
No.
You're plugging in 2/3 right there. 1 plus 2/3 is, we got 5/3 in the numerator, right?
And
And in the denominator, what do we have? 2 plus 2/3, which is going to be,
8/3.
8/3.
Wow, I'm so fast in that.
and then what?
So it's gonna be 5/8.
5/8. So we went 1, 2/3, 5/8, and then the sequence continues. So you got to feel for the sequence, right?
Yeah.
monotonically.
We're trying to prove that this thing converges
11,
to
13.
this. Okay? There's 2 steps to this.
Is that the square root of 5?
Yeah. So there's 2 steps. Don't be worried if the answer's coming out where you're like, what the heck, that's messed up. Don't worry about that for a second. We're trying to evaluate the limit of this thing. There's 2 things that we need to do first. 1, we need to prove that it does have a limit. That when we take the limit, we're not breaking any rules.
13 over 20.
And then 2, we need to figure out what that limit is. Does it make sense that those are our 2 steps?
Yeah,
Okay.
21.
Am I just talking to Janetta here?
Sorry.
2-step, we're trying to evaluate the limit of this thing.
Yeah.
There's 2 steps to the process. 1, we need to show that the limit exists. And then once we know that limit exists, we're going to figure out what the limit is. Okay?
Hey,
Okay.
the way you figure out the limit exists is by
Proving that it
using
converges.
monotonically
Can you read that?
decreasing.
Yeah, we need to show if this thing is bounded and it's monotonically decreasing,
We know it converges.
then we know it converges. Right? If a sequence is only getting smaller and smaller and smaller, and we know it never gets smaller than some number, it's going to eventually converge. Maybe not to that number, but to something. Right?
So yeah,
So,
we know it's monotonic.
1. Well, first start with it's always positive. So it's bound from below by 0, right? So here's how I say that. Observe that if a sub n is greater than 0, comma, then a sub n plus 1 is greater than 0. Maybe put the comma there. Right?
So it's always.
If this is a positive number, then this is a positive number, right?
Yeah.
Comma. And so since
N is.
a sub 1 is greater than 0, comma, a sub n is greater than 0. If you say it like that,
I know.
does that make sense?
See,
Our first term is greater than 0. And if our first term is greater than 0, our second term is greater than 0. And if our second term is greater than 0, our third term is greater than 0. I could have written this out as a whole proof by induction, but I'm not going to take time to do that. Hopefully you can just make this leap.
Yeah, that makes sense.
It makes sense. Yeah.
Okay,
I
you
forgot
follow.
proof by induction. I think you already did some of those.
Alright, 2. So,
Question real fast. What if a sub 1 was not positive? What if it was negative? It'd
Has-
still be bounded
Has
because
to be.
if that was your first term.
we were just trying to find the lower bound.
Genius.
That's all we were trying to do.
Yeah.
In this case, it was easy to show it's bound from below by 0.
Mm-hmm.
If it started out with some negative term and then was increasing, I could say whatever that first term is what's bound below by.
Okay.
Okay, now we know it converges.
No. Now we know it's bound and below. We need to show it's monotonically decreasing.
Oh, I thought we already showed that.
How do you show a sequence is
The
monotonically
next
decreasing?
term is less than the previous term.
Right, we need to show that the next term is always a smaller number than the previous term. How do I show, what's one way that I can show that A is less than B? I can look at A minus B and see if it equals a negative number. If A minus B equals a negative number, I know that A is smaller than B.
But how do you prove that big picture? Because I was having a problem.
I'll show you how to do it, but
Well,
make sure you understand this logic because this is exactly what we're doing.
okay, so you're saying if you have an.
Good.
Okay, say that
Do
again.
it
If,
inductively,
if A is
or
a
you
smaller
can
number than
work
B,
with A sub
then A minus B is a negative number.
algebra those.
Up at the top.
If A is bigger than B, then A minus B is a positive number,
Okay,
right?
yeah, well,
So I'm going to use the exact same thinking. I'm going to look at A sub n plus 2 minus A sub n plus 1. The next term minus the previous term.
It's gotta be.
Oh.
If this thing comes out negative, it's decreasing. If this thing comes out positive, it's increasing. If this thing comes out 0, it's a constant. And then if the sign can't be determined, then this thing isn't monotone.
okay,
Okay?
That goes out positive.
yeah,
Well, we'll see how it comes out.
Quick question.
Oh,
I don't see how you can take two terms in the sequence and say that. I know you're saying n, so it's any term really.
Right.
But
that's,
all the time you have sequences with an oscillating value.
if we put
Right.
it for n though.
If you can do it for any two terms in the sequence.
That's what that's saying.
Right.
In the same.
If you had an oscillating sequence and you tried to do this, then you wouldn't be able to evaluate the sign.
Right.
Whatever comes out. So if you try seeing, okay, I'm trying to prove that this thing's monotone increasing, and then you end up with a big mess that you can't do anything with, and maybe you made a mistake thinking it was monotone increasing.
Okay.
We won't be able to prove something that's not true.
Right.
does,
Can't- That's a good way to say it. If you proved it, it's true. So it works.
No, where I was confused.
I know
was
how
n
you're
being
confused.
any number.
I know where you're confused. We're not showing that there are two terms that satisfy this. We're showing that any two terms satisfy this. Right. Okay. So,
question, instead of doing that, can't you just say that because the denominator is larger than the numerator, then it's getting smaller?
This is how we would.
no, that just means that it's less than 1. How do I know that the 10th sequence in this thing is smaller than the 9th sequence in this thing?
Oh,
The 10th term in the sequence is smaller than the 9th term.
We have to show for all.
Yeah, you can check the 10th one, now check the 11th. And if you check all the natural numbers that way, then you're good. And you don't have to do this.
Yeah.
So your choice. You can do it in possible task, or you can do it this way. Maybe there's a third. Alright, so let's prove this. Alright, what is a sub n plus 2? That is 1 plus a sub n plus 1, oops, plus 1, over 2 plus a sub n plus 1. So there's a sub n plus 2,
okay,
minus
1 plus a sub n.
1 plus a sub n over 2 plus a sub n.
That seems unnecessary.
Seems unnecessary?
Seems like you could just do a sub n plus 1.
It seems like your a
You
is
probably
gonna be
could.
bigger.
Should we try it that way?
Yeah.
I didn't try that.
It's not gonna.
Let's see what happens when we just do
Time you
this.
pick an n and then go into that set and find that n. The bigger the n, the
So
smaller the
get a common
number. So the bigger
denominator.
before.
Oh.
Is it
No,
going to be
what?
busy?
Yeah, exactly.
So look,
The bigger the n, the smaller the number.
Yeah.
Oh, right. Okay.
Plus 2a sub n plus 1 plus a
Oops,
sub n plus
that's a
1
plus
squared. Oh, minus a sub n plus 1 squared.
That's the 2, right?
Right.
And now I'm doing minus a sub n plus 1 squared. Now I always evaluate the side of that thing. We got negative 1. But I don't know if the negative of one of those minus that is going to be bigger than the 1. I don't know how to handle that. So, it's a good thought.
It probably takes some other thinking, like you'll have to explain that a sub n plus 1 squared is less than 1.
So let's see, what does this equal? So here we get, getting a common denominator, I've got 2 plus 2 a sub n plus 1 plus a sub n plus, those stupid plus 1s keep throwing me off. 2 plus a sub n. I'm gonna run out of space doing this, huh? Let me just write it on the next line. It's easier for me to look that way anyways. Okay. And maybe we'll just take the time to write it out to make sure I don't have anything in space. 1 plus a sub n plus 1 times 2 plus a sub n minus 1 plus a sub n 2 plus a sub n plus 1 all over 2 plus a sub n plus 1, 2 plus a sub n. Right?
You can factor out.
Now I can't factor anything out.
You can.
I can distribute. What can I factor out?
They're all unique.
Okay, can't you factor out? We'll distribute, okay.
Those are two very different things. Alright,
In fact, they're opposites.
so 2 plus a sub n plus 2 a sub n plus 1 plus a sub n plus 1 minus, geez, I wrote way too big. Minus 2 minus 2 a sub n. You guys gonna be okay if I just skip down there?
Yeah.
Minus, let's see, I did 2 a sub n minus a sub n plus 1 minus a sub n plus 1 all over 2 plus a sub n plus 1 2 plus a sub n, which equals,
Does everything not cancel?
no, not everything, but some things should cancel. So let's see, we have 2 cancels out with negative 2. That goes out.
Negative 2an.
an plus 1, an plus 1 goes out.
See, Mark, couldn't you have factored out
So now you
2 plus
have,
a?
2 a sub n plus 1
now you have a negative a
minus
sub
a sub n plus 1 is a sub n plus 1. So we have an a sub n plus 1.
On the right side?
and you have a,
That takes care of this term and this term.
Can't you factor out an from
And you have an
an
an.
plus 1?
And then we have an an minus 2an.
so minus an.
Even if you did, you'd be left with a mess in place of that.
an plus 1 minus an, is that what I got here? Yeah, okay, so we didn't make any mistakes. So it's that over 2 plus a sub n plus 1, or is that a 2? No, it's 1, I'm having more 2's. Times 2 plus a sub n, right? Okay. Now, this is kind of weird thinking, same thing that we did before, so follow it real quick. The difference of these two is negative when the difference of these two is negative. Right? When is this term negative?
When.
This whole thing is negative when the numerator is negative,
Right.
because all the numbers are positive, right?
Right.
So all we care about is when is the numerator negative.
Right.
So this an plus 2 minus an plus 1 is negative when an plus 1 minus an is negative. So the third term minus the second term is negative when the second term minus the first term is negative.
Mm-hmm.
And what is the second term minus the first term?
Second term is n plus 1.
We have 2/3 minus 1, it's negative 1/3.
Yeah, there.
So it's monotone decreasing.
Just because you proved one.
Well, look,
And it's
for any two terms,
Oh,
they're decreasing if the previous two terms were decreasing, right?
yeah.
So the first two terms were decreasing, which means the next two are decreasing, which means the next two are decreasing, which means the next two are decreasing.
when they're in.
Okay.
Same type of thinking again.
Wait, can you do that with every single sequence?
No, only with a decreasing sequence or an increasing sequence. They have to be monotone, otherwise you're going to run into a situation you just can't solve.
See, so if it's monotonically decreasing and the first two terms are decreasing or negative, then can't you just say it's monotonically decreasing? If you think it's monotonically decreasing,
We're proving it's monotonically decreasing. You can't use the fact it's monotonically decreasing to prove it's monotonically decreasing. Right?
okay.
Okay. Okay. So, that was a lot of work to say, it converges. What do they converge to? Well, now let's find that out. Now we're going to use this theorem over here, which says that the limit of a sequence and the limit of a subsequence are the same thing.
What's
Right?
the subsequence of this?
A sub n plus 1 is the subsequence of a sub n.
Okay.
Right? It just starts one term later. Instead of starting with the first term, it starts with the second term.
Alright.
So,
Yeah, but to prove a sub n plus
Okay.
1 converges,
5. Then there exists a such that the limit of a sub n equals a, right? That sequence converges to something. That is the limit.
no, a sub n
And we're
plus
going to call it
1.
a.
Okay.
Huh?
A sub n plus 1 converges.
So does a sub n.
Okay.
We just proved that a sub n converges. The sequence converges.
No, we proved a sub n plus 1 converges.
No, we didn't. We proved the sequence converges. We proved that a sub n is bounded below by 0, and that a sub n is monotonically decreasing. That's what we proved
Okay.
so far. Which means it converges. Whatever converges to, I'm going to call it a. Now I need to prove that a is equal to negative 1 plus the square root of 5 over 2. What? How am I going to do that? So then, look at this equation. Then the limit of a sub n plus 1 is equal to the limit of 1 plus a sub n over 2 plus a sub n. Right? Take the limit of both sides of that equation. Good?
Yeah.
Alright, let's find out what that is.
Fine.
What is the limit of a sub n plus 1?
A sub n plus 1 minus that is the absolute value of that is less than
What is the limit of a sub n plus 1?
A sub n plus 1.
a.
It's just a.
A.
It converges to the same thing that a sub n converges to. That's what we proved over here.
Right.
They converge to the same number. A sub n sub k and a sub n both converge to a.
Okay.
So over here, a sub n and a sub n plus 1, which is a particular subsequence, both converge to a. So, not equals, I'm doing an arrow over. So that gives me the limit of this, A, is equal to, we know how to evaluate the limit of this. I'm not going to break it up into all the steps, but it comes out to 1 plus A over 2 plus A, right?
Yeah.
Right? The limit of the quotient is the quotient of the limits. The limit of the sum is the sum of the limits. The limit of the constant is just a constant. The limit of A sub n is A. You can use all those rules, break it out, do the limit of all this, and we know it comes out like that, right? Great. What does that give me? That gives me that 2A plus A squared is equal to 1 plus A. That gives me that, move this over, we have A squared. When we subtract an A from both sides, we just have 1A left. Minus 1 is equal to 0.
Okay.
Good? Just moving everything to the left-hand side.
Okay.
And just writing it in decreasing order of powers. And now, that gives me that A is equal to -1 plus or minus the square root of 5 all over 2. But we know that A has to be greater than or equal to 0. It can't be negative, right? So, we can't have the minus sign there.
We never got taught how to do that in this
Hold
class.
on, wait. No, that's just.
Well, that's just an algebraic property.
Yeah, but thought we had to build everything.
Do you not know how to prove this?
Prove that. No, I don't. That an equation equal to 0 has two solutions.
You don't know the quadratic equation proof.
No, you do.
Yeah, we didn't.
Well, yeah, we've seen it.
But you don't know how to reproduce it?
I have no idea how.
Don't try to reproduce
Try
it.
to reproduce
Okay,
that.
see if you can do it. So you start out with ax squared plus bx plus c equal to 0.
It's all algebra.
And it's going to be, you're going to use completing the square. Yeah, you don't need any new axioms or anything like that. But yeah, if you can't prove that, try and prove it. And if you're stuck, talk to me after school.
I'm trying to get, what am I trying to get to one side?
You're trying to find what x equals.
You kind of.
Right? So you're going to use completing the square, there's a big hint, and you're going to end up with x equals negative b
I know. Okay,
plus or minus.
what do you mean
square.
completing the square?
Huh?
What does he mean by completing?
Go watch a YouTube video on completing the square.
Complete.
Is it just
It's.
Finding the terms that give
Yeah.
you, just go
finding-
watch a YouTube video. I don't want to take a half hour to
I
give you
know,
a shot
I've
to the
got it.
square. And if you're stumped,
You've done it with
I'll do it after school
polynomials
with you.
too.
I wish Sal Khan taught like Bucky Roberts. Hey, what's up, everybody? Today we're completing the square. You put two triangles together.
No, I never thought about it in terms of geometrically. I need to go rethink about that geometric interpretation of that.
Oh yeah, that'd be interesting.
My stomach is swollen.
Okay.
My stomach is swollen.
Anyways,
Yeah, I was in Sunday school.
so there's that. Next idea that we need to come across is the idea of a peak index. Okay?
Like, I
Uh,
guess one.
Peak index. You have a good idea so far. A peak index
The best.
is an index where it's an index in the sequence where every term later in the sequence is smaller than or equal to that. So let's pretend I'm just graphing a sequence for a second, even though.
So like
It's
our
kind of a
peak
weird
index
thing to
would be
do.
1.
So let's graph one, and let's say the sequence comes out like this, 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 this, and then from here on out it keeps decreasing. Right? There's my sequence. Here's a peak index. Pretend I started this at 1. We don't have a 0 index. Sorry. Here's a peak index because everything afterwards is smaller than or equal to it. So here's a peak index. Here's a peak index. Pretend that these two things are the same thing. Here's a peak index because everything after it is smaller than or equal to it. This is not a peak index. Here's a peak index because everything after it is smaller than or equal to it. Here's a peak index because everything after it is smaller than or equal to it. Here's a peak index, here's a peak index, here's a peak index, here's one, here's one, here's one, here's one, here's one. You see what I'm saying? That's what a peak index is. It's an index such that every term in the sequence from that index onwards is smaller than or equal to that term.
Okay, question. In this proof that we just did, the peak index would be 1 because they're always decreasing, right?
Every term in the sequence is a peak index because it's always decreasing. Monotone decreasing sequences have infinitely many are completely peaked. Sure. That's nice. You're always at the peak.
My life is a monotone.
So I'm always at my peak. So I'm always getting worse. And then a monotonically increasing sequence is the exact opposite.
Never.
There is no peak index.
Okay.
Unless, of course, it's just a constant. I should say that. If it's strictly increasing, then there is one. Oh no, there never is one. Unless it's a constant, then everyone is one.
What if it goes like this? What if it goes like this? Then right here, wouldn't right there be a peak index?
No, because later on it increases.
Oh, right.
So unless there comes a point where it's constant from there on out, then it doesn't happen. So peak index, that's what it is. Now let's write it out. Definition. We call M a peak index in a sequence A sub n if for all n greater than or equal to m, A sub n is less than or equal to A sub n.
Why'd you explain to us peak index before you defined it?
Give you intuition for what it means and then give you the exact definition. So you feel like that makes sense?
Yeah.
Take any index bigger than m, the thing at that index is smaller than or equal to the thing at m.
Okay.
Good? Alright. Now let's do a proof using this. And the proof is every sequence contains a monotone subsequence. Yes.
Does magic down my face.
This is a long way from that song. What does in mean to you?
My presence, I have.
I mean your face.
If I mean your presence, I mean you.
Yeah, it's actually saying. Stop
I
flipping
mean
me off.
your face.
Guys, just get ready. You didn't get the vibe and emotions.
If the intensity of the sound wave is
Present in my eardrum.
no greater than what's the unit for sound?
Decibels.
Is greater than
1
3
decibel.
decibels by the time it gets transferred into an electric signal to my
What
brain.
is intensity?
Then it's in my ear.
Is it
It's joules
energy?
per
Then it's in my face.
square area.
Energy per area or per volume?
Per area.
Mark,
Area.
it's in
Area.
It's the surface
Yep.
area of the sphere.
Makes sense. Alright. Every sequence contains a monotone subsequence. What does this mean? Pick a sequence that doesn't converge.
Negative
One,
1 to
yeah.
the end.
Negative 1 to the end, what do we get? We get 1, negative 1, 1, negative, well, depending on how you start it.
Dude, that would be such a cool proof.
So what we're proving is that every sequence you pick, I can go through and just pick out terms, get a subsequence, I can pick out infinitely many terms, get a subsequence that is monotone. So this one's not monotone increasing or decreasing. But I can go through and pick that one, and just pick ones.
Even the cosine function actually makes no sense.
And the subsequence I would get is monotone.
You could find multiple monotones, so you can substitute
Well, that makes
in
sense.
every sequence.
So every sequence contains at least one, and yeah, you can get infinitely many because take one that's already monotone and then just cut out the first term. Still got the second term. Still monotone.
But you
It's infinitely many long, so you can drop infinitely many terms and still have an infinite sequence. Infinity is a fun number. It's not a number. Well, it's an extended real number, I guess.
That's why it's fun. It's tricky.
Let's harvest.
But it's not a real
It's not a number.
Let's harvest the energy of something going to infinity.
It's not a real number, is what I should say.
Harvest the energy of something
Harvest the
going to
energy of
infinity.
something going to infinity.
A black hole.
We fire something off at escape velocity, it'll go off to infinity. We harvest that energy. We don't get infinite energy.
That is one of the coolest problems that you do.
It's so
So one of the problems that you do in physics, one of the funnest little problems to help keep your intuition, is shooting a rocket into space.
Or a
How much
meteor.
fuel do I need to shoot a rocket so that it will pretend that there's nothing in the universe except the Earth? How much fuel do I need to put in a rocket to shoot it off so that it will go off into space forever and never come back? Now this is kind of weird because the gravity of the Earth is pulling on the rocket the entire time. So the rocket is slowing down. So I need to give it just enough speed so that the rocket is always slowing down but never actually
The
stops.
limit of the velocity is 0.
Wait, Earth's gravity has an effect on that rocket even after it's light years away.
Yeah. Just light years worth of gravity, which is small.
That's true.
So that's called the escape
Is that
velocity of
possible?
something.
But what?
Yeah,
That
that's
is
how we
so
get our
cool.
rocket to the moon. We have to overcome the Earth's escape velocity.
I know.
Like,
But-
it's actually pretty easy to
What I'm saying is it's possible to send a rocket into space if nothing existed.
If it was just here, yes.
And it would never retain.
No
And it
matter
would never
where
come
you are,
back.
I will always
That's
fill your
literally
pool.
not possible.
Sure it is.
It's
You just need,
getting slower.
it's getting slower and slower and slower, so let's make something that might represent the velocity of the rocket. Let's graph it. The
Yeah.
velocity of the rocket might look something
There's
like
parts
this.
of the universe that are so far away.
And at
between
infinity,
us
the
and
velocity
from
is
past
0, and it stops at infinity.
that we will never fill their pole.
Well, when did it get to
Pole
infinity?
only travels at a speed.
Okay, bodies.
That is
So someone
ridiculous.
says, James,
That's a
everything impacts
Huh?
everything. It's all connected. And you say,
Well,
well,
that's
if I don't
yeah,
affect
convergent.
you, you don't affect me.
Right. The velocity converges. So you give it its velocity, and you give it enough so that when it converges to
I
0
would use
as
that.
you gravity
Stamps
acts on
that all the time.
That is legit.
it. It is legitimate.
Oh my god.
See the space between us, it's expanding.
Alright.
Yeah.
Huh?
And then you say,
Should
I have it on camera. I'll figure
David,
it out.
and you say, David, when I was so tonight,
Take it out right now.
Yeah, use your mind powers.
Why would I say
All I
that?
have to do is
If I'm not observing it.
just
video.
to them.
Okay, I bet your Apple has some way of retrieving videos.
The other cool one is if there's an asteroid out to infinity and it starts moving towards Earth, there's a limit on the energy it will have when it impacts the Earth.
That makes sense because you can't make it go. You can't.
No, it's out to infinity
Start an asteroid at infinity.
with a velocity.
And now it's coming towards the Earth. And it's speeding up. And it's speeding up, and it's speeding up, and it's speeding up, and it's speeding up, and it's
I
speeding up.
thought objects can only hit a certain point.
Well, you're thinking of terminal velocity. There's no air in.
There's no air resistance in space.
So in space, things can accelerate without.
That's why when things come into the atmosphere, they're burning up. They're going faster
Than terminal velocity.
than terminal velocity. And so it's all that friction with the atmosphere that's creating the fire and
But
burning
if
it up
there's
and
an,
ripping
there's
off
an
the pieces of
asteroid
it.
infinity away, starting at 0 velocity, and the Earth pulls it a little bit, and it speeds up from infinity away, gets faster and faster. There's a limit on the energy it will have.
Because there's a limit on how fast we can get. It's the reverse of the same idea.
Because I thought you can't get faster through light.
No, it's nowhere close to the speed of light.
It's not going to be the speed of light.
It's
It can't
actually,
reach the
like,
speed of
it's
light.
not that much energy.
I know it can't.
Not even taking into account special relativity, though.
Like,
There's
assuming
still-
it could, it can't.
That is cool. But
Alright, let's get back to this proof.
But what?
the
So,
objects have to hit a certain point where they can't move at a certain speed.
well,
Well, it's kind of like falling from the.
anything with rest mass can't move faster than the speed of light. It can't even move the speed of light.
Yeah, can't even. speed, right?
Right. If it's traveling the speed of light, it would be photons.
But you're saying it's constant, isn't close to the speed of light.
Right.
What the asteroid would hit the Earth with, yeah, it won't be close to the speed of light.
Its escape velocity, which is nowhere near the speed of light.
Okay. So let's look at a sequence. So we're proving every sequence contains some monotone subsequence. So even if you have some crazy sequence doing all sorts of random crap, we're guaranteed that there's some sequence that we can choose out of there that's a nice monotone sequence. We like monotone sequences, right? They're nice. So notice that there's two cases. So if A of n is any random sequence, then one of two things. Either there's infinitely many peaks, or there's not infinitely many peaks. Right? That, are you still wrapping your head around what we're doing?
You just got
You good?
We have to do both cases probably.
Yeah, we're going to handle two cases.
If it's
Two.
If it's monotonically increasing or decreasing.
No. Pick any sequence. It doesn't have to be monotonically increasing, it doesn't have to be monotonically decreasing. Just pick any sequence.
Okay.
Either it has infinitely many peak indices or it doesn't. Right? It either has finitely many or infinitely many. We talked about the sequence 1, negative 1, 1, negative 1, 1, negative 1.
Mm-hmm.
That has infinitely many peak sequences, or peak indices. Every time a 1 comes up, that's a peak. Right? We talked about an increasing sequence. That doesn't have any peaks.
Monotonically increasing.
Monotonically increasing might, but if it's just increasing, it doesn't have any peaks.
zero finite.
Is zero finite? Yes. Anything that's not infinite is finite. Not finite is what infinite is.
I wish it was unfinite.
Good? Alright. So let's handle the easy case first. There's infinitely many peak indices. So assume A sub n has infinitely many peaks. Call them, I don't know, n sub k. So n sub k is the sequence of indices that were peak indices. So when we were doing 1, negative 1, 1, negative 1, it would have been 1, 3, 5, 7, 9, etc. You with me?
Okay.
Okay, so every single one of these are peak indices. Then A sub n sub k, A sub n sub k is monotonically decreasing. Right? If every term in your sequence is a peak index, then it's monotonically decreasing.
Yeah.
That make sense?
Yeah.
Okay? So let's make sense of that again. A sub n had infinitely many peaks. Make a subsequence out of just those peaks. Now you have a monotonically decreasing sequence. Nice and easy, right?
What about,
Okay.
oh wait, monotonically means less than or equal to.
Less than or equal to. Correct. Alright, 4. Now assume A sub n has finitely many.
You don't
Maybe
need
a finite number.
Do you need to create a subsequence for this one? Because it does seem like you need to.
I need to create a subsequence for both. I need to show that for any sequence, I can create a monotone subsequence.
Oh, right.
Right? That's what we're proving. Now assume a sub n has a finite number of peaks, comma, with the last peak at some index n. How do I know this thing, how do I know I can find an index where the last one occurs at?
From some index onward, you never find it.
Because it's finite.
Yeah, there's finitely many of them. So there has to be a last one. Right?
Yeah?
Any finite set of natural numbers has a max element and it has a min element. Remember that?
That makes sense.
Pretty sure we did that.
We do.
I think we did that with integers in general. Any finite set of integers, or I think we said bounded set of integers, which, if it's finite, it's bounded. Okay. Da 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 da. 5. Then index n1 equal to n plus 1 is not a peak. And what does it mean for it to not be a peak? So
There's some number bigger than it after it follows.
perfect. Then index n1 equal to n plus 1 is not a peak, comma. And so there exists n sub 2 such that n sub 2 is greater than n sub 1 and a sub n sub 2, or n sub 2, right, is greater than a sub n1. Right? Similarly, there exists a sub 3 such, or n sub 3 such that a sub 3 is greater than, or a sub n sub 3 subs is greater than a sub n sub 2 with n sub 3 greater than n sub 2.
Right.
And so now we can see it in general and then write our final proof, or write our final statement. In general, for any index n sub k, comma, there exists n sub k plus 1 such that n sub k plus 1 is greater than n sub k and a sub k plus 1, a sub n sub k plus 1 is greater than a sub n sub k. Right? For any peak index you have, or sorry, for any index that we know is not a peak, we know that there exists some other index greater than it that gives you a term greater than it, because it's not a peak, right? I'm just generalizing what we did here and what we did here. In general, that's how you get it. Are you seeing it all?
Yeah.
Therefore, a sub n sub k is a monotone
because I'm sitting here confused because if you have if it's consistently going up, so if it's monotonically increasing, then you won't have
Has
any
no
peaks.
Right.
Zero.
And we're dealing with that case.
Oh,
Zero. Yeah.
okay. That's where the 0 comes in. Yeah, you've got the right thought there.
That's the case that you don't need to do anything for it because it's the whole subsequent, the whole thing already satisfies being monotone.
No, it doesn't. Just because there's no peaks.
Well, they're saying let's look at a monotonically increasing series. It has 0 peaks, therefore it's monotonically increasing.
Is that what they're thinking?
Okay.
Because just because it has no peaks doesn't necessarily mean it's monotone, right? Simple example to think about would be n times sine of n. Something like that. I don't know if it'll work with natural numbers, but for real
Right,
numbers, you can see
anything
it.
that wavers as it
Anything that
goes
wavers and
up.
grows. That's going to get big, and alternate the time.
If you have a sequence that is constant, would you say it has infinitely many peak indices?
Uh-huh. So, if it's a constant, it has infinitely many peak indices, meaning every indice. So then we can make a subsequence where we pick every indice. There we go. We made a monotonically decreasing sequence. It's a constant sequence. Still works. Okay? Now let's do a proof. Every bounded sequence has a convergent subsequence. Maybe you can just see how to do this one.
Subsequence?
Yeah, what is that? I don't get what it's trying to say.
Pick a sequence, any sequence that's bounded.
Place it
Okay.
in the
You
middle.
can find a subsequence.
I can find a subsequence that converges in there.
Oh,
That's what we're saying.
well, okay. Didn't we prove that, oh, it's only in dense.
Since it's bounded and it's monotonically, then we know it's a convergent sequence.
Perfect.
It's almost a lemma.
Not a lemma. Corollary.
Correlate.
Lemma helps you prove corollary immediately follows on the proof.
Is that bonus proof?
Right? We already know that every bounded monotone sequence converges. Oh, that's not what we proved today, but we used it here.
Wait,
That's what they proved in the homework, probably.
It's limit based
We
on.
did it last
we
week.
did it in our homework. Or last week, yeah.
We did it last week, 2.3.
Yeah, so hopefully you remember that.
Yeah, it's still is.
Yeah.
If it's monotone and it's bounded, it converges. And so, there we go.
Oh, just 2.4.
Another definition, sequentially compact.
Probably get to section 4 by the end of this semester.
A set of numbers S is said to be sequentially compact provided that every sequence AN in S contains a subsequence that converges to a point in S. Okay, that one's kind of a mouthful. So let's wrap our heads around it real quick. So the property we're defining here is sequentially compact. And we're going to find out that this is basically the same thing as closed for the scenarios that we're talking about. Closed is sequentially compact are going to turn out to give us the same thing. But a set of numbers S is said to be sequentially compact provided that every sequence in S, you remember what it means for a sequence to be in S?
It means
All the A sub n terms are in S. Right? So S is some set of real numbers. We take some sequence A sub n in S. If that sequence, for any sequence we take out of S, if it contains a subsequence that converges to a point in S, then it's sequentially compact. So we've got S. Randomly pick a sequence out of S.
that converges.
No. S. Pick any sequence out of S. Any one you want. If for any sequence you pick out of S, you can find a subsequence that converges to a point in S, sequentially compact.
Why is that important?
Hold on. Okay. You have a set S and you take a
Sequence out of it.
sequence out
Any
of it.
sequence you want.
Okay, so then if this set, the subsequence converges.
If you can find a subsequence, if there exists a subsequence of this sequence
Okay.
that converges to a point in S, then it's sequentially compact.
Okay.
So here's how it works. Here's a set S. You pick a subsequence out of it, right? Any one you want.
Okay.
Or you pick a sequence out of S. Then I have to look carefully for it in it to try and find a subsequence in there that converges to a point in S. If I can do that for any sequence you pick out of S, then it's sequentially compact.
Okay, so you have set S, and then you have a subset of that, A of n, then you're saying in a
That needs to
subset-
be a sequence.
a sequence of,
Where all the
and
terms
you're
are
going to
S.
find a sequence in my sequence that
Yeah,
converges to
subsequence.
S.
That converges to a point in S.
Okay.
Does that make sense?
Yeah.
Alright. Let's look at stuff that is not sequentially compact real quick. To try and help us wrap our heads around this. Proof. And I told you it's going to be, turns out sets that are closed are sequentially compact. But let's use this real quick to do a small proof. Prove the set S equal to, what did we do, from 0 to 2, like that, is not sequentially compact. How do I prove it's not? I need to say, here's the sequence, and it doesn't matter what subsequence of this you take, it's not going to converge to something in S. Okay? So,
Obviously, that's very much possible.
right. Let AN, and what are we going to use?
1 over n.
1 over n. Comma. And let A sub n sub k be any subsequence. Two. Then, what's the limit of A sub n sub k?
The limit of A sub n.
Is A.
Right? We already proved that if a sequence converges, every subsequence of that sequence converges to the same thing. So here's a sequence that converges to 0. Any subsequence you pick of that thing, I don't care what you pick, it's also going to converge to 0.
And it's not.
So we proved this isn't sequentially compact. Because I found a sequence such that for any subsequence you take of it, we converge to something not in the set.
Okay, so let's go over sequentially compact again. Every sequence.
Yes, so it's sequentially compact if for any sequence you pick, I can find a subsequence that converges to something in S. How do you prove it's not sequentially compact? You say for a set S, there is a sequence such that for any subsequence it does not converge to a point in S.
Seems like it's pretty rare interval. Well, like if 0 was inclusive, would that be a sequentially compact?
Yeah, 0, if that were a closed brace, then it would be sequentially compact and it would also be closed. And so we're going to prove that sequentially compact and closed give us the same thing. How good of a place would this be to take a quick break? Oh no, closed and sequentially compact aren't the same thing for infinite sets.
Well, you don't have a plus if you don't do infinite set. Oh yeah, you do.
Yeah, we'll go ahead and take a break, and when you come back, we'll finish this section, and we'll start continuous functions.
Guess what?
What?
If we start continuous functions, then we did more than we were planning on to today.
Okay.
Again, freaking number.
That's a new world record.
And I bet
Oh, is
I
that?
can guess. No, I bet I can guess what your number is in up to 2 guesses.
Up to 2 guesses?
Yeah. Okay, so pick a number.
Okay, I did.
Okay. Is your number 1? No. Okay, so that means your number is that. Is that your number? No. Listen, is this your number?
No,
Then this is.
everyone.
Your number is not 1.
That's not.
Yeah, it is.
That is.
Or that's not.
There's only one.
That's programming 1.
Yeah.
That's programming 9. So any sequence in that interval converges to an element of that interval.
So
If it converges.
any sequence in here is bounded, right?
Bounded infinite sequence converges?
Well, it's bounded, doesn't mean converges, but since it's a bounded sequence, it contains a monotone subsequence, which is then a bounded monotone sequence, which converges. And then since it's in AB, then it converges to a point in AB, because we know that AB is closed.
Alright, I'm trying to make a bigger statement on that. Trying to see if we can. Any converging sequence in AB converges to an element of AB.
Yeah, that's what we meant when we said that's closed. So we're using that already.
But any convergent sequence is monotone, so I'm saying the same thing as that.
Not any convergent sequence is monotone.
Or has a monotone subsequence.
That's true. But it just needs to be bounded. Any convergent sequence is bounded. Any bounded sequence contains a monotone subsequence.
So what I think I can say a little more than that is saying the exact same thing as that. I have a feeling I'm gonna be in a math class one day and I'll be proving something like that. And I'm gonna use this proof to prove it, and it's gonna be way different than the intended proof.
Yeah, if you do a topology class first, then you can prove things topologically, and then they happen to also be true in the topology on real numbers. So, for example, we're about to come up with a definition of continuous. And in topology, a definition of continuous is a very simple thing. So if I have a set, 1, 2, 3, a topology on that set is a set of subsets, call it A to save me from rhyming. A topology is a set of subsets on that set where it contains A, it contains the empty set, contains the whole set, contains the empty set, and then for any other set you put in here, the only restriction is you have to, the union of them has to also be in there, and the intersection of them has to also be in there.
For it to be continuous.
For it to be a topology. Topology is a special type of subset,
Okay.
or a set of subsets. So this right here is a topology by itself. That's a topology.
Because you
On
have
that.
the union and you have the intersection.
Yeah, the union of those two is in there, and the intersection of those two is in there. But I could have also thrown in the set 1. We still have a topology.
Because one union,
One union
One
that is just
union
1.
that is
One
one.
union that is
Union
just
that is
A. That intersect, that's the empty set, that intersect, that's just 1.
right, okay.
So that's another topology. So there's tons of topologies that you can make. A continuous function in its simplest form. So it's a function, so pretend I've got, this is topology 1, and I make some other topology 2, which is equal to some other set. So when I have a function from topology 1 to topology 2, oh, sorry, not that. T1 is defined on A1, and topology 2 is defined on A2. So I take A2 and create some topology with A2, right? So if I have a function from A1 to A2, we call it continuous if the pre-image of every open set is open. So pick an open set over here. If the things that map to it are one of these sets, it's continuous.
One of those sets. But
Yeah, so if I have over here, let's create a
in
set
an open set,
A2, the empty set.
and so.
And then let's say that this was equal to, we'll do an easy one, 4, 5, 6. And then we put 4 over here. So then I create a function. Let's see. F is equal to, we'll map 1 to 4, 2 to 5, 3 to 6. If I view f as a function from, so I say f is from A1 to A2, defined by where f equals that. And then it's a continuous function.
What does it mean for a pre-image to be open? Or
Oh, the image is the output.
image?
So all the possible images here would be the set 4, 5, the set 5, 6, the set 6.
Okay, what does it mean for that set to be open?
If it's in the topology, it's an open set. A is open, the empty set's open, the set containing 1's open.
Okay.
Over here, the open sets are A2, the empty set, and 4. So take the pre-image of each of these under this function and see if it gave you an open set. The pre-image of 4 was just 1. Yep. The pre-image of the empty set was the empty set. Yep. The pre-image of A2 is A1. Yep. So the pre-image of everything here is something in here. And it's not necessarily that everything in here has to map to something in here. It's the pre-image. It's kind of unintuitive. Why is it that way? That's kind of weird when you first come across it. But if the pre-image of every open set is an open set, it's continuous. And that's a perfectly valid way to think about continuity even when you're doing calculus. And so it could be easier as you're going along to think about open sets this way as opposed to, or continuity this way as opposed to what we're about to do.
Well, I just have someone one day I'm going to be doing some proofs on a closed interval, and I'll be like, hey look, this interval is sequentially compact, and this sequence is in that interval.
Break another window tonight?
This sequence has a subsequence that can reduce this.
Battery is low. We should probably fix that. Your computer isn't meant to.
Does it stop charging when it's asleep?
No, I think that port was just having an issue.
Okay, last time we ruined the video because we couldn't tell if it was charging. So.
It's on cold.
Here,
Does-
Put your hand on it and see if you can feel that.
When it hits above 73,
Right, so
it
now-
blows cold air.
Yeah, now we can turn it on heat.
Does it vibrate when it starts charging? I
Should.
didn't feel anything. Maybe the screen will light up.
72.
Here, I'll just check to see if it's connected here. That seems to be it.
You will sync your library.
Well, I'll just
Now
see if
we're
it
just
shows up.
low set
Can I
kill.
sync my library?
Exactly.
Now when it gets
Connected with
below
an authorized
72, it'll
cord.
heat up.
Yeah.
What's
And
wrong
if
with
it
it?
got above 72, then it'd blow out cold air.
Yeah, it's because when we walked in, it was 75 degrees.
Look, turn it up and it makes the air hotter.
Just turn it
No,
up 1
just-
degree.
Someone's filter's clogged, so air's not getting across the coil, so moisture around the coil is freezing through the coil and the filter block by. So I come to the person and I say, hey, your coil's frozen out. I'm like, oh shoot, I knew I shouldn't have turned it down that much.
You think they're supposed to understand that? I mean, that makes 100% sense.
When the coil's supposed to handle being that cold anyway, right?
Wow. You turning the temperature down
These
on the
are the
thermostat
best
doesn't
days.
make the air any colder.
The best, and I could not agree more. Cloudy days? Hey, I love sunny days. Cloudy days depress me when it's a whole bunch, but
Did you say cloudy days depress you a whole bunch?
when it's a whole bunch, like a whole bunch in a row.
I,
Yeah, it's 'cause he's messed up.
I
Yeah.
live in
We have
Seattle
a
just
little
so
bit.
I can live in constant cloud.
No, sun is actually way better.
Direct sunlight is, no one likes it.
Direct sunlight
There's almost never a case where direct sunlight feels good.
Well,
actually
yeah,
feels
special
so
case.
good. That is my favorite weather because I feel like I'm getting like sunny D.
Oh my good laws, you are.
Maybe it's just because I sunburn more than
Yeah.
But these
Summer's
days
the
make me
worst.
want to huddle up in my room and play Modern Warfare. No, not Modern Warfare, the Zombie Z game.
Makes you want to huddle up in your room with a nice whiteboard, a good expo marker, prove some stuff.
You're not wrong. It makes you're not wrong. Anything really.
Just as long as you have that big blanket around you with hot
Homework
cocoa.
is better during the winter.
with those apple cider packets.
Without
Yeah.
the side, right?
10 bucks say we have outside our dinner.
I just barely bought a box. That stuff's so good.
Outside
That
of
stuff's
cocoa.
addictive. packets?
I know what you're talking about.
That stuff is freaking cocaine, dude. I drink
The
one
apple
cup,
cider we
and I
had
have
for
to
our
convince
activity
myself
was so
not
good.
to make another.
Are you
You
serious?
do?
It's like
This stuff is so good. I can just keep drinking it.
I actually should tell you the story of my apple cider life. Every single beverage of apple cider I've ever had, I burned every taste bud on my first sip, so I can't even taste
Yeah,
it
that's
for the
like
next.
stove apple cider.
No, on that one because it's so hot.
The apple cider we had for our activity was so fluid.
Yeah, I burned my
You do the
taste
same
buds on
thing
that.
with hot cocoa.
I know. I
You
did the
should
same
do
thing with
that.
hot cocoa, but not with coffee.
Yeah, unless you're not lactose intolerant like James.
You're lactose intolerant. What an unfortunate life.
James, remember?
Only a
what
little
you
bit.
did?
Only a little
Eat
bit.
some cereal with milk right before Sunday school.
I don't know why my stomach just randomly swirls.
I can tell you.
James watches Donnie do a proof that's a little bit off. Says something's not sitting right. I don't know if it's the milk.
I'm a little bit lactose intolerant. I'm not
I think
full
Yeah.
blood.
You and Emily.
most people, when they eat dairy, have some like mental effects.
It's normal.
Are you trying to justify?
Actually, majority of the world cannot digest milk.
All right,
Yeah.
True story.
and we're done with that. Now, let's do one more proof, and then two more proofs, and we'll move on to chapter 3. Continuous functions, the second big idea in this class. So, quick proof one more time. Let's prove that 0 to infinity is not sequentially compact as well. So, the sequence I'm going to pick is just n, right?
Okay.
Nice and simple.
It's not bad.
Yeah, so then that is ns and it's not bounded, right? If it's not bounded, it doesn't converge. We understand that?
Yeah.
Right. And then any subsequence of this is also not bounded. Right?
Mm-hmm.
Is that true?
Yeah.
Yeah, obviously, because it goes to
Right, it goes to infinity. I mean,
you already showed us that, a subset of infinite
the
series.
nth term in the nth term in any subsequence of this is greater than or equal to the nth term in this. Right? I mean, I could have probably written that out again, but we've already covered that logic once.
Yeah.
I'm saying, so we're taking a substance. Here's the sequence. 1, 2, 3, 4, 5, 6. The subsequence, whatever term I put here, is always greater than or equal to the corresponding term up there. The smallest thing I can put here is 1. I can also put 2. From here on out, it's always greater than or equal to that. So if this thing is never bounded, this thing is never bounded. Because for it to not be bounded means that for any index you pick, I can find an index in this bigger than the number you picked. If I can find an index in this bigger than the number you picked, I can find a number in the one same index is also bigger. But, anyways, so there you go. There's a sequence and it's unbounded, and since all subsequences are unbounded, none of its subsequences converge. Therefore, they don't converge to a point in S. So it's not sequentially compact. Now let's prove that things of this form are sequentially compact. Okay?
Okay.
Was the break a bad idea?
No.
Did I just lose you guys?
No,
We're out of
That
everything,
makes
we're
sense.
back in. We're good to go? Good? Alright. So now the interval AB, let's prove that that is sequentially compact. So remember what that means. For any sequence you pick, I can always find a subsequence that converges to a point in that interval. So let xn be any sequence in AB. Now since x ends in AB, it's bounded, right?
So it's
It's always greater than or equal to A and less than or equal to B, if it's in there.
Yeah.
Mm-hmm.
So it's bounded. And so if I have a sequence that's bounded, it has a monotone subsequence. Call it x of n sub k. Every bounded sequence has a monotone subsequence. That was the last major proof we did, right? Okay. So then x of n sub k is bounded and monotone, and therefore it converges. Right? X of n is bounded, and so it contains a monotone subsequence, x of n sub k. Then x of n sub k converges. Why? Because it's bounded and it's monotone. right?
Wait, why does it contain a subsequence?
A monotone subsequence.
X of n is bounded.
Because
You good with that?
Yeah.
You could always find a,
Every bounded, you're right.
Okay, that's what I needed. Every bounded.
every bounded
Converted.
subsequence.
Every sequence contains a monotone subsequence, we have that. And every bounded sequence has a convergent subsequence, we have that.
Okay, there we go. That's it.
So I've got a convergent subsequence.
That's also monotone.
Oh, I didn't even need to say it was, oh, we didn't know if this thing converged. I've got monotone and bounded, which means it converges, right? So x of n sub k converges. Now, x of n sub k is also in AB, right? So it converges, and it's in a closed interval.
Right.
So it converges to a point in that closed interval. That's what we meant when we said that thing was closed. If every convergent sequence converges to a point in that sequence, if every convergent sequence in that interval converges to a point in that interval, then that interval's closed. That's what we proved.
Right.
I think it's theorem 2.22. So since this converges, and since this is in AB, then the thing it converges to is also in AB. So big picture, what do we do one more time? Here's an interval. We picked some arbitrary sequence in the interval, and we found a subsequence of this that converges to a point in the interval. Sequentially compact. Good?
Yeah.
Yeah, question. If a sequence is bounded, then you can say that it converts. Okay. So right there we said bounded sequence are okay.
Right here.
This is where I'm trying to get. If you prove that it's bounded, then you can prove that it converges.
Hold on. You're skipping a step. Every sequence contains a monotone subsequence. So, if we have a sequence, we have a monotone subsequence, right? Okay, now looking at my sequence that's monotone. If it's monotone and it's bounded, then it converges.
Right.
Okay, so can you just say it's bounded? You have a sequence that's bounded, so it converges.
You have
Because every sequence contains.
it has a convergent subsequence.
Right.
Every bounded sequence has a convergent subsequence.
Yeah.
But the sequence itself doesn't have to be convergent.
Right? I got 1, -1, 1, -1, 1, -1. That's bounded. That doesn't converge. But I can find a subsequence in there that converges. 1, 1, 1, 1, 1. Or -1, -1, -1. Okay?
Okay.
Alright. Now, moving on. So I told you that there was going to be 4 major concepts that you have to get comfortable with in this class. The first one was the idea of a limit. The definition of a limit. Never goes away. It's here to stay. Forever and ever and ever. The next big idea that you take on in calculus is the idea of continuity. The idea of a continuous function.
Isn't it like, aren't we going now from sequences to functions?
A sequence was a special type of function.
Okay.
We were keeping it easy, keeping it light. Just looking at ones whose domain is the natural numbers. Now we got to put on our big boy pants.
No.
Start dealing with functions from real numbers to real numbers.
So, are we transitioning into chapter 3?
Yes. We're skipping 2.5, by the way. You got
You
to
never
do
did
that.
that one. Oh, that is.
This
Yeah,
is
yeah.
chapter 3. The
Now chapter 3, starting with this definition.
Wow, way to start chapter 3 at the bottom of it.
I know.
That's giving it exactly what it deserves.
He's
Okay.
being continuous in his writing.
Now, let's make sure we understand this notation. We went over it in the beginning, but you've got to get comfortable with this notation.
Imply for.
We do not have time to keep going over this notation with you over and over and over again. So make sure it makes sense. A function f from the set D to the set R. This is its domain, and its image is a subset of this. Okay? You might remember that we went over this before when I told you anytime I have f from A to B, there's some information you're given right out the door. F is a function which has a specific definition. The domain of f is equal to A, and the image of f is a subset of B.
Okay, I don't get that. What's image of it?
Yeah, what do you mean?
So we went over this in the preliminaries.
Probably.
Not probably, we definitely did. the image of f. So what is f? What is a function ultimately?
It's, you put a real number in and then.
No. What is a precise definition of a function?
It's a sequence. It's a special sequence.
No. A sequence is a special function.
Isn't
What's a function?
isn't it a set of numbers where
It's a
No, it's not a number.
it has
It's
a
an equation.
unique
It's not an equation.
Set of pairs.
It's a set of
Ordered pairs.
ordered pairs
where what?
where
So f is equal to a set of ordered pairs.
Where x goes to y.
where you have a
Where
unique
every
Oh yeah, I remember where every input has a unique output.
Is that a function?
yeah.
No.
No.
One goes to 2 and one goes to 3. Pivot that 2. There. Now it's a function, right?
Yeah.
No. 2 goes to 3. 2 goes to 4.
3 can go to the 7.
Now it's a function, right?
Yeah.
3 goes to itself.
Yes.
Good. That's a function. A in this case is 1, 3, 2. B in this case is, we don't know, but it at least contains 2, 3, and 4. Let me give you another function to get you comfortable with this idea. Well, let's look at the function from R to R, and I told you when we went over this, that in all your algebra classes, every time you saw f, it was assumed that you were going from the real numbers to the real numbers. So you didn't write this out because that was always the case. You weren't dealing with other types of functions. So f from R to R, where f of x equals x squared.
Okay.
The domain is R, but the image of this function is 0 to infinity, which is a subset of R. Okay?
Would you not call that the range?
Sure. I'm going to say image. Get comfortable with image.
Yes. You could. I'm just saying.
Yes.
If
Okay,
they're
yeah.
almost, if they're identical, or.
Right. So this is called the domain. This is called the codomain. The part of the codomain that the function uses is called the image.
That's the subset of the.
So the image is always a subset of the codomain. It's always a subset of that right side set. So a function, f, and anytime we use this d, the reason this d is for domain, it's understood that this is a subset of real numbers. Okay?
D is right.
Yeah, it's some subset of real numbers.
Okay.
So now we're looking at real value functions. Why isn't this always just r? Why aren't we going to be always talking about functions from r to r?
You know,
Well, let's look at a function like this. No! That doesn't work! What does f of 0 go to?
Undefined.
Undefined. So then, later on in your algebra courses, they said, find the domain of a function, is what they told you to do, instead of just assuming that the domain was all real numbers. And so what's the domain of this function? What's the biggest domain we could use? Everything but 0. So this is a function from the set of all x in R, where x is not equal to 0, to the real numbers. Right? Getting comfortable with it? So that's why we have this d here. It might not be all real numbers. We gotta be careful. Some numbers might break our function. Okay? So, a function, f, from some domain to the real numbers, where the domain is also real numbers. It's just not all real numbers. Okay?
It's a subset.
So, a function f from d to r is said to be continuous at some point in the domain x naught, provided that whenever xn is a sequence in the domain that converges to x naught, then the image of that sequence, f of xn, converges to f of x naught. Now this should look vaguely familiar. We did something a lot like this when we were talking about polynomials. You remember that big polynomial proof that we did?
Yeah.
We were essentially proving that all polynomial functions are continuous. That's what we did. And you can go back and rewatch it in that light. It will help you get understanding. But that's what it means to be continuous at a point. Now, the function f from d to r is continuous. We call the whole thing continuous if it's continuous at every point in the domain.
Okay, let's go over continuous at one point here.
calculus or whatever to
There's
begin
no
with,
hole in the graph.
that when is it continuous? It's continuous if I can draw it like this without picking up my pencil, right? Or marker. That's what it means to be continuous, is the notion that you were told. It's not very precise. It's not very accurate. This has a very precise definition, and you're going to see that this ends up being true, and this leads to another way that we describe continuous functions, the epsilon delta definition, which you might have seen, which helps us understand how it translates here. So it will capture the same intuitive idea. This ultimately leads to that. But there's a definition. I think the best way to get real comfortable with it is start proving some things are continuous.
Okay, before you move on, will you go over it one more time?
Yes. So a function
Mm-hmm.
whose inputs are d and whose outputs are all real numbers. Not every real number, but its output is any output, some set of real numbers, right?
Okay.
So a function from some domain to the real numbers is said to be continuous at a particular point in the domain, provided that any sequence, I jumped down a line, provided that any sequence xn in the domain that converges to that point x naught. So I've got my domain, maybe do a picture as we're doing it. So here's d, we'll make a some closed interval. Pick a point in there, x naught, okay?
Okay.
Now pick any sequence in here, xn. Pick any sequence in here, xn, so that the limit of xn equals x naught. Pick any sequence where that's the case.
Okay.
If it also happens to be the case that the limit of f of xn is equal to f of x naught, then it's continuous at that point. So pick an x naught and pick an xn that converges to x naught.
Okay.
So that this is true.
Not is it specific, like 1 or 2.
Oh yeah, sorry.
First element.
Are you guys not comfortable with me saying x naught?
It's just like a specific.
X sub 0 and x naught are the same thing.
Okay.
It's how you typically say it in, I don't know, do you typically say that in math classes?
Yeah.
Yeah.
I got it from physics.
Yeah. There we go.
Okay. X naught is just some number, some real number in the domain.
Is R naught.
From here on out, we like to use x's to be in our domains when we're talking about real numbers, and y's to be in our image if we're talking about real numbers. Okay? So same way that I always use n as a domain for a sequence, I'm always going to use x's as a domain for a real value function. Does that make sense?
Yeah.
So anytime it's x, you should be thinking in the domain. So pick some number in the domain, and pick some sequence that converges to that number. Okay.
A sequence that converges to the domain. Or
A sequence in the domain that converges to that number.
A sequence in the domain.
Yeah.
Oh, and then over here we're looking at ranges now. Or
Yeah.
images. Okay.
Then, if the limit of the image of the function, the image of that sequence, converges or equals f of x naught, then it's continuous.
So both cases happen.
So if this being true implies this is true, continuous at that point.
Okay, makes sense.
Okay, and you're saying we're using our domains are our x's and our images are y's, right?
Typically, that's what you do, yeah.
Okay.
So anytime you see x's now, you should be thinking in the domain.
Okay, and our domain can be anything, right? Natural numbers.
Any subset of real numbers.
Okay.
Typically, it's going to be an interval of some sort, or some combination of intervals. So let's prove that something is continuous. And we'll prove some polynomial is continuous. And we'll just do it from all rails to all rails. That's perfectly valid. What's polynomial?
X cube.
2x. Yay! We do the same.
Alright, let's prove that thing's continuous.
Okay, first we have to prove that there's a set of domain that converges to a certain point.
Let x naught in R. Pick some point in the domain. know that R is dense, so I know that I can always find some sequence that converges to it, right?
Mm-hmm.
Some sequence in it though?
Yeah.
Okay.
So xn is some sequence in R that converges to x naught, right? I don't know how many steps I need to break this out into for you. I think you're good just going straight to this, right?
X naught.
Yeah. You good with that leap? Or do we need to break it down in? Let's do one where we break this down all the flipping way. Where was it?
X sub 2.
Oh, thank you. Right? That's f of xn.
Okay, I see where you're getting the X naught.
Equals, now hopefully you can see this. X naught cubed plus 2 x naught over 7. Good?
Because the limit of each of those.
So we proved that the limit of this sequence, or sorry, the limit of f of this sequence is equal to f of x naught. Therefore, it's continuous.
Wait, are you using there that the limit of a product is the product of limits?
Yeah, I'm using that the limit of
So,
the sum is the sum of the limits, and that the limit of a product is a product of the limits. I'm using both those.
What am I getting stuck on?
So I could have broken this up into the limit of that plus the limit of that plus the limit of that. And then I could have broken this one up into the limit of each of those individually plus the limit of those individually plus the limit of that. Then the limit of a constant is just a constant. And then we know the limit of x band is x naught.
I can see everything fit into place now. Or old proofs.
Good. Does that make sense?
Mm-hmm.
so my question is a similar question to when I had at the start here. We are saying we're letting a series or a sequence converge. How do you just let that happen?
We're picking a sequence that converges. Pick any sequence you want, as long as it converges to x naught.
Oh, okay.
Doesn't matter what it is.
Probably makes sense. Yeah.
Good?
As long as it's in our, or in our domain.
Right. For all we know, this sequence is just x naught, x naught, x naught, x naught, x naught, x naught, x naught. Who knows? Who cares? It's just some sequence that converges to x naught.
So the idea is you prove it's continuous on the domain, and also.
No! If, for any sequence in the domain that converges to x naught, the limit of the function of the sequence, the limit of the image of the sequence, converges to the limit, or converges to the image of x naught. That's continuous. We're showing that, here's the smallest way I can think to write it. The limit of xn equaling x naught implies f of xn, implies the limit of f of xn
Is
is equal to f of x naught. If
Oh.
this implies this, continuous. Anytime this is true, continuous. How do I show it's not continuous? I show this is true, but this isn't true.
Right.
Right? There's only one way to show a false implication. There's 3 ways to show it's true. Vacuously true means we can never find this is the case, therefore it's
Okay,
continuous.
then will you prove that 1 over x is not continuous?
1 over x is continuous.
No, or.
Well, at what point?
From real to real. Right, because 1 over 0?
Oh, it's not defined at that point. So you can't say it's not continuous. I mean, it's kind of a weird thing to say. That 0 is not in the domain of that function. You can't have 0 in the domain and have a function. So 1 over x isn't a function.
Okay.
Here's a function that we can make. We can make f x is all reals where x is not equal to 0 to the reals by f of x equals 1 over x. Ah, now we have a function. If I let 0 be in the set over here, I don't have a function anymore.
Because you're not.
Because
mapping
0 can be-
Because then that means somewhere in there I have 0 comma what? What does this term look like?
Calculator says und.
I can't put that in the function.
Okay.
So what you're talking about is a case where you don't have a function. It's kind of bad language that we use all the time. You think anytime you see an expression like this, you have a function. No. This is shorthand, and we assume that you mean the domain's this, since it's the only bad point. But you're making a lot of assumptions when you say this is a function.
But if you had that where, and then you have a special case where 0 is mapped to 1.
Right.
That's a function that's.
So if I say, you could write this something like this, and we could make a function. F of x equals, and we say 1 over x, where x is not equal to 0, and we say 1, where x is equal to 0. Okay, there's a function.
And it's not continuous.
And this one is not continuous. It's not continuous at 1.
Because
Okay.
it's not indeed.
Okay, now.
Because if I look at 1 over n, 1 over n goes off towards n. Should we show, let's prove that this is not continuous. So let's do this one.
The limit is infinity, but the value is.
Observe that 1 over n is in the domain, right? For this function. F right here defined, it's from R to R. So prove not continuous. So let's prove that this is not continuous. You understand the function we're talking about?
Yeah.
Do you have roughly what this looks like in your head?
Yeah.
Do you have what this looks like in your head? 1 over x, when we plug in really big numbers, we only need to see what half of this looks like, so we'll just look at half of it.
Big
1
numbers are
over x,
small.
big numbers are really small, but if I plug in a teeny number there, it's massive, right? So it looks something like this, but then at 0, we gave it a value of 1.
So we fill
Right?
in one empty spot.
And then with the negatives, you have the reciprocal. I don't know, reciprocal's kind of weird word for that. You have the reflection of it, right?
Inverse.
And so that's our function. And your brain should tell you it's not continuous right there. Because there's no way for me to go from drawing this to drawing that without lifting up my pencil. So we're in trouble. That was the stupid intuition that you were given in college. Not stupid, dumb down. No, what's the next way to say it?
Arrow said it's stupid, but
This is intuition. Okay, so observe that 1 over n, this sequence, maybe put this around here to make sure we understand it, is in the domain, comma, and the limit of 1 over n is equal to 0.
Sorry, it's not.
We're proving that it's not continuous at 0. This is the x naught that we're talking about. We're going to prove this function is not continuous at 0. Okay? So remember how we show it's continuous. We show that the limit of xn equals x implies the limit of f of xn equals f of x naught. So, to show that this isn't the case, we need to find out where this is true but this is false. I'm saying that's going to happen with 1 over n. 1 over n is our xn. Sorry, this is x naught. And x naught is 0. So this is true, but this is going to be false. Okay? So then, let's see. We're doing the limit of f of xn is equal to the limit, and maybe to help like you slowly ease into this, I'll break it down into more pieces. F of 1 over n is what xn is, right? Plug that into x, and is 1 over n ever 0?
Yeah.
No.
What n do I plug in that
Or
gives me
sorry.
0? No. So, this function is always 1 over whatever we plug in. Or in other words, it's just n.
1 over 1.
F of 1 over n, which is 1 over 1 over n, is just n.
Yeah.
So you see how f of 1 over n is n in this function?
Yeah.
Which is loosely talking infinity, which is not equal to 1, which is equal to f of 0.
Boom. Not continuous.
So it's not continuous at 0.
So limit of 1 over n equals 0.
Why did you say it's not equal to 1?
The limit of
That's what f of 0 is. F of 0 is 1.
N.
So I'm showing that
The limit
the
of
limit
1
of
over
f
n.
of x naught is not equal to f of x naught.
So the limit
This was
of
infinity.
our sequence is 0.
This was
The limit
1.
of the function of our
Oh.
sequence.
Infinity is not equal to 1.
And you're saying our x
So
naught
the
is
limit of f of xn did not equal f of x naught.
Why did we get it?
So we had, huh?
Why do we get to say that 1 over n is the number?
Is in the domain. I'm saying, look, here's a sequence in the domain that converges to 0.
Okay.
Okay,
So I have a sequence xn that converges to 0, but f of xn did not converge to f of 0.
Okay, here's where I'm getting confused. Where you're taking the limit of f of 1 over n is equal to the limit of n.
Okay,
You just have to write it out.
let's look at our function. What happens when I plug in 1 over n into it? I get 1 over n, right? 1 over x.
Oh, okay.
Good?
Yeah. Okay, now I have a question. If you have a function, okay, so you're saying it's continuous if you don't include x, right? Or if you don't include 0.
No. 0 goes to 1.
Oh, I'm saying, okay. Before, when you have the domain be
Everything but 0.
everything but 0
Then
to the reals, then it was continuous, right?
it was continuous on that domain, yeah.
Yeah. So what if you make your domain where it's like,
What do you mean kind of?
I don't know if this is gonna make sense, but if you have a function that's like two things that is, okay. I need
Well, it has multiple points of not continuous.
yeah, multiple points of not continuous, but in your domain you specify not at 1, 2, 3.
Then yeah.
And it's not continuous at 1, 2, and 3.
Yeah.
So you have a function that's not continuous at 1, 2, and 3. And you don't have the points 1, 2, and 3 in your domain. Then you have a continuous function. What's a
Yeah.
continuous function? It's a function that's continuous at every point in its domain. If you get rid of the points in its domain, that's not continuous at. It's a continuous function. A continuous
So if
function
your
is a
domain
function
is
that's
like-
continuous at every point in its domain.
It's crazy.
I don't know how else to say that.
If you okay,
Look,
Because before x was not in the domain, right?
right, 0 was the only bad point. So if you take 0 out of the domain, then yeah, it's continuous everywhere. Because the only point you were worried about is 0, and you just took that out of the domain.
What if you, okay,
So it's
what if you
continuous
took-
everywhere
What
in
if
the
you
domain.
took every number out of the domain except for like 2 numbers and they were continuous at that 2 numbers? Then you say that that function is continuous.
It's going to be continuous, but it's going to be continuous in a vacuously true way.
Okay.
Because, so let's have the function f of x. Well, actually, that's kind of tricky to say. Yeah, it's not straightforward as I was thinking. Well,
What's the
it could be
question?
with a weird case. I was going to come up with a function that only has 2 points in its domain, or in its range, but it's also continuous. And I don't want to make something messy. So, never mind, forget about that.
Okay.
But there's a
But
definition.
in theory, it'd be continuous, right? You could say that it's continuous.
You
And
could
those
create one
2
that is
points.
continuous,
It's the thing.
even though its output is only 2 points.
So
Probably. I'd have to think about that. Maybe there's no way to do it.
Because if you take it out of the domain, then
Actually, of course there's a way to do it. Sorry.
Constant.
Yes, it's very easy to do. But it gets into a weird idea of continuity that you're not comfortable with.
okay.
So I won't do it. Because I'd be doing just a finite set to a finite set. By mapping 1 to 1 and 2 to 2. That's my whole domain, that's my whole range.
Oh, it's over 6 class.
So, that's the idea of continuous. Here's what I strongly recommend. Go back to find the video where we went over the polynomials. Where we were taking the limit of sequences and taking the limit of sequence of a polynomial. Because exactly what we were doing in that class is proving that every polynomial, the limit of every polynomial is continuous. That's what we did.
So we're about to do that proof now.
No, we did it.
We already did it.
We already did that proof. So the author jumped ahead, so that when this stuff came up, it was like, now it's easier. You stretched your brain really hard to wrap your brain around that polynomial proof. Now we're just looking at nice, easy special cases, and this should be nice and easy for your brain after wrapping your head around that polynomial thing.
Now my
So-
brain is loose and baggy.
So go rewrap your head around the polynomial thing, make sure that makes sense, and then this stuff will be a lot easier if you can wrap your head around that. Okay, let's call it there.
Why do I feel like
Are you
it's
back to school now?
I don't know. I am still hurting.
Did you last time?